my great privilege to introduce VC, who needs no introduction. I've worked with him for 30 years. He always has some new and interesting ideas about every other day. And so, VC, I'd like to invite you up to present your Patterson Award lecture.
I would like to thank you very much for this opportunity and kind introduction. I'm honored and humbled to accept the 2008 ACA Patterson Award. I would also like to thank Dr. John Rose and Dr. Garrett Newton for organizing this symposium and arranging for the distinguished scientists to speak in this session, and for all of you attending this special symposium. The title of my talk is Resolution of Phase Ambiguity in Macromolecular Crystallography 25 years later. I will spend about 2/3 of the time on what I have done and why I did it 25 years ago. For the rest of 1/3 of the time, I would like to talk about the impact of that early work on our recent efforts for achieving routine software phasing for macromolecular crystallography. And this second slide, I would like to give a brief summary, although Dr. Hector's already mentioned, that summarized by the life of Dr. A. Lindo Patterson and his contribution and impact in crystallography. Patterson was born in the year 2002 in New Zealand and died in Philadelphia at age 64. He was the faculty in the McGill University, MIT, and Fox Chase Cancer Center. I thought this would summarize the work he has done and the contribution in the foreword of the Patterson and Patterson, 50 years of Patterson function. This is by the President IUCR, Theo Ham. It said it was a milestone in the development of the young science, the crystallography, because when in 1934, L. Patterson's first paper on the F-square series appeared. The Patterson function has opened entirely new avenues to the solution of crystal structures and continue to be a widely used tool. This was in the mid-1980s. This is the book, the symposium held at the Fox Chase Cancer Center, Philadelphia, for the 50th year of the Patterson function, and this book was published in 1987. And here, this is the one from that book that here's how is the Patterson function in his handwriting. You see here he used A, but my novel calls to copy with an E. And here, this explains the interpretation of F function, because you can see the convolution of the X and X plus V vectors. There's a vector here, and F squared. And here is the list of the previous winner of the Patterson Award. And I'm very happy to be in the company of these scientists. I'm honored that Dr. Wang Henderson, the first winner of the Patterson Award, is a speaker to celebrate this occasion. Dr. Herb Hauptmann accepted Dr. Rose and Newton's invitation, but could not make the trip. Instead, Dr. David Lenz will give a talk on their joint work. Dr. Hai-Fu Fan of the Chinese Academy of Sciences also accepted the invitation, but could not come because of visa problems. His former student, Dr. Wang of the Macromolecular, will give Dr. Fan's talk. I'm also honored that other distinguished scientists took their time to come and present talks at this symposium. Perhaps I should start my talk with the wonderful early years in learning crystallography. Crystallography was a subject completely new to me when I started my graduate work at the University of Arkansas in 1963. The university is located in Fayetteville, Arkansas, which is near the Ozark Mountain. Not only the environment is pleasant, the study in the laboratory of Dr. Wally Cordes was a delightful experience. For those of you who know Wally, many of you know, you will agree with me that he was such a wonderful teacher. After graduation, I was fortunate enough to go to the lab of Dr. Richard Marsh at Caltech for my postdoctoral training. Both Wally and Dick were great fans of Patterson function. Some of you know that. The Patterson method was the only method we used at the time to start structure determinations. Both Wally and Dick have greatly shaped my life and career today. I would like to use this opportunity to give my special thanks to them for opening my mind and give me an appreciation for the beauty in crystallography. In 1970, I moved to Pittsburgh, first at the Department of Crystallography, then moved to VA Medical Center. There I was asked to work on immunoglobulin-related protein crystal structure. Without previous training in protein crystallography, I started to read publications in this area. After about a year and a half, I was fortunate to crystallize the Bernstone protein RHE. That diffracted 1.6 angstrom from home source and solved the structure in about 9 months using data from 2 heavy atom derivatives and anomalous scanning data from one of the derivatives, which is a gold derivative, which I later on use a lot of tests with that derivative. So I thought that the protein crystallography was not as difficult as most people believe. But my luck ran out very quickly. In the process of determining the structure of the second protein that I crystallized, which is the PAB. Only one isomorphous heavy atom derivative was found after 1.5 years of searching and testing over 100 soaking conditions. Each of those conditions would take 3 to 4 days at least of work to find out if it were isomorphous, because you had to take the precision photograph after dry, compare the intensity, see whether you can reverse or any other sense. So that's when I realized that I need to learn again more how to use single isomorphous derivative data. So the learning cycle start again. After understanding the nature of the phase ambiguity problem, I thought that an alternate procedure for obtaining a noiseless SR map then might be possible. So that's how, since this idea was something like 1980 at that time. So first I would like to maybe I can see better if I come here. Just to review a little bit about the phase ambiguity that at that time when we understood from 19... Oh.
Hello.
Okay, can you hear? Yeah. During the 1940s to 70s, that kind of, so from the page 153, the Blundell, the Johnson book, it says that let us assume that we have measured FH and Fp, and that we know the arrangement of a heavy atom in a crystalline unit cell. That is, we can calculate the vector Fh. What can we then derive about the phases? Using the cosine law, we will have this. That means alpha p here equal to alpha h plus minus. The equation shows that there are two possible values for h, which cannot be distinguished from one isomorphous derivative. So in the page 157 to 78, that there are two closely similar ways of including the phase information from single isomorphous replacement in the Fourier synthesis. The mean of the two, that means this is considered 0, can be used with suitable weighting. This Brew and Rossman, 61. Alternatively, both phases can be used in Fourier calculation. They use both of this. This is known as double-phased Fourier. This is Byford in 1947 and Brookhaven et al. In 51 talk about this. Now here's interesting. It can be shown that the synthesis using single isomorphic replacement are actually equivalent to protein structure plus the inverse structure convoluted with the phase square structure of a heavy atom. It's Ramachandran and surrounded by Singh in 1970. If the heavy atom also in the non-central chemistry position. This method can then give a protein electron density map, as was shown by Brew and Rossman, but a high level of background has meant that it has been really used by protein crystallographers. So it's quite so that's the explanation. But I was intrigued by this sentence here. The protein structure plus the inverse structure convoluted with the phase square. I said, what does that mean? so I began to draw a picture, trying to understand it. This is one of the early drawing in the picture, and then so you have two phases here. So I draw it this way. This is here, and this side here. This is FH, and here. So immediately this will become clear. SIR equal to alpha H, and RSI is alpha H pi, because if we assume this vector is projection of AP on this one here, you can see if this is longer than that, projection on the other side, if this shorter than that on this side. So this equation was in the literature already become very clear to understand that. This is not the first time I derived, but it was there, so I can understand it. So if we follow this some more, if this is the correct solution, this is a false solution, F, this is like this, this FH. So we have two. So we use the mean like that. If we continue this derivation, sure enough, I have an equation like this. What this is, the protein. But here is interesting, it's a protein, but here is alpha P, but it's minus. So suddenly it occurred to me, oh yes, this is the inverse structure, but with phase square this structure, heavy atom. You see this heavy atom is 2 because the exponential is square. So now this is perfect, it was completely correct. Now finally I understand what they're talking about. So we have this equation here, and if you transfer this as put a weighting scheme on here, and you do the Fourier synthesis, you get this map. This is a perfect protein map. But this noise reason, because there's no correlation between that randomly. You can run that phase. That's what it is, the noise about. So now I understand why it has been really used by protein crystallographers. So it's not very helpful. Just confirm that probably why people don't want to use it. Now, this is from here. But if we arrange this, put the protein on this side, you find the rho minus noise. So by this, then I was thinking about it. So my attention was then shifted. How about building a filter to remove noise? Remove this noise by filter. So that was the thinking in the 1980, that time. So in the next few years that I was working on that, but at the beginning the filter was not very good, but it seems very promising. So I'll report to you on the progress by removing the noise. The first one I reported in the international meeting in Canada, Ottawa, I called protein phase determination by the single isomorphic replacement method with the phase solution and refined process. So I thought this is not really good, but at least it's better than that. And 82, in the winter meeting, by the way, at that time the ACA has 2 meetings a year, winter and summer. Winter meeting, I wrote presented a talk on the Patterson Macromolecular structure by an iterative single isomorphic replacement method. And in the summer meeting, in San Diego, I said Patterson macromolecular structure by iterative anomalous scaling. So it's not just an isomorphism, but getting to anomalous scaling, and a fully automated procedure for accurately define the protein solvent boundary. And then also that year, I was invited to give oral presentation at a Golden Conference. It was invited by Jones, because he saw that brochure, and so he called me. And in 83, I combined these 2 isomorphisms, so I said included an integrated program package for Patterson SIR or single wavelength anomalous scattering in the small mass. So by that time, since I'm dealing this with phase ambiguity in SIR and SS, and also quite a success in SIR data. So I thought perhaps this approach is probably good enough that we can call, if not the perfect, but at least some way for resolving phase ambiguity. So I present this in the Hamburg, the international meeting called Resolving Phase Ambiguity in SIR and SS data. So when I wrote up the publication, this is the title, which is published in 85. So this process, then in this here I have a key diagram here, and this side is SIR. So this is the derivation that I just showed you before, but also include the SAS. Because between them I realized we can treat the SAS just like a SIR, similar. Now, but the question is, how can we treat the SAS in a similar way as treating SIR? That's a question. I did not really explain in that article. So in order to do that, then we think we need to look at the so-called phase triangle relationship in SIR and SS. For SIR, easy to understand because FP plus FH is phase triangle. But SS is hard. This actually is not quite correct. But it's useful representation. Why? Because we know that F plus is F and heavier native plus heavier is so this factor. But F minus should not be there, should be below this thing here. But if we rotate this, flip over, you see the imaginary axis on top and on the bottom, then we have this one here. Then we use this translate to here. This F double prime, this distance plus distance, that's what 2. Form this triangle. If we accept this kind of rotation, then these 2 cases are very similar, we can treat as similar. So some years later, then in the lecture in the summer school crystallography, I was used this way to explain it. I said basic principle of SR and SS method is to find the orientation of phase triangle from the orientation of one of its sides. Because triangle we have 3 sides. If you fix this one, the orientation either this or flip over, just like this one here. So this is what phase ambiguity problem. So this makes the procedure much simpler. Conceptually derive any equation will be easier. But keep in mind, this is not really right, but just it's a representation. So we may treat SAS data similar to how we treat SR data because we know how to treat SAS data by that time. So the proposed noise filtering process for resolving phase ambiguity is like this. You use the original data, that like say SR data. You calculate the Fourier phase, transfer to the direct space here, condensed map. But I use this information to make a filter. And that goes here. This phase, this map should be better than before, then calculate phase information, and then filter. So the map getting better, and also the false phase beginning event gradually to filter down. So that's what the idea. Now the important part is that building this filter is your own data, no additional diffraction data. So it's all contained inside here. So some years later that I made this statement, the phase ambiguity problem. The phase ambiguity is not an inherent property of single isomorphous replacement or single anomalous scattering data. Why? Because this view is analogous to the phase property in crystallography. In this case, phase loss occurs for individual reflection when only intensity is measured. But phase loss is not an inherent property when intensity is the plural of a complete data set. This is the basis for the right method. We track the phase information within even the neighborhood of so it's all there. For phase ambiguity occurred individual reflection pair. In fact, only one reflection, and then we have two measurements. Then that's lost. Phase ambiguity is not an inherent property when the intensity of a complete set of it. No. In other words, everything's in there. And therefore, if we measure a set of SIR or SI data accurate enough, and I will emphasize accurate enough, then the phase ambiguity problem can be solved without additional data. That's not for the reason that I feel very strongly, very early, single wavelength is enough. So now we said that how can noise filtering, this sound fragmenting, because sound fragmenting had people use that word before. What I did very similar. The only thing that I did was to build a filter, so communicate like this word. So how can we? That's it. The two ways to answer it. One is conceptual. Sound fragmenting can locate and enhance the protein image. That is, whatever is not solvent must be protein because two parts. From the protein image, the phase of the structure factor of protein can be calculated. And once you calculate, then what? This calculator can then be used to select the true phases from the false phase. That is, if you divide this part, if the calculator phase on this part, then I select this, like that. So that in essence, the phase ambiguity is resolved by the phase image itself. So that's conceptual. Now, so this is the one is the ISS map from experimental GO data. I mentioned that I've retrieved on GO, RG. So this you can see, this is a real data, not the calculated data, how clear it was. This is 3 Armstrong map. The second one is a numerical solution by iteration. That's what I put iteration in front of the word called ISIR. Let's start with SS map. Let's FS is equal to this plus this. But if the molecular boundary is known, then noise can be separated into 4 parts. This part plus this part. This part is in protein region have positive density. This is in protein region negative density. Some region positive negative. So we can consider this as filterable because some region shouldn't have a very high, so we can remove it, filter some way. And the negative, we should not have a negative. We should have some negative, but not that much. So this term become filterable. So first filter map, then you remove that. So say you get that and here. Then after filter 1 and cycle 1, then this spread out, and then same time the filter mirror increase. So the filter pattern are getting smaller, smaller, smaller. So at the cycle, this can become smaller. So this become protein. So that's the numerical way to look at it. Now the critical part is locate the molecular boundary for making the filter. Here, let's say. Electron density map represents the population electron because electron is the fundamental of atoms. It is useful for locating the atom, but not good for locating the molecule. If we want to locate the molecule, we should have somewhat like an atomic density map. A circle is needed to represent the population of atom. To define the molecule in the same way that population houses define the city. Even though you have a good house, tall house in some place, which is a lonely one, is not considered city. So the population is important. A new map is constructed such that density equilibrium is the sum of positive density within the sphere R equilibrium. So to the density, we have to define the size. So this kind of map. This map tells the population of finding the boundary between the molecule, city, and so outside the city. That's kind of idea. So if we look at it, this is electron density map. From the molecules, not from the another map. Another map is calculated from this map, from the volume, This point is all those points summed together by this one here. The weighting skin is like this. Itself is highest, but gradually it comes. It's a linear weighting skin. I found that a linear weighting skin or a curved skin make no difference. Linear skin easily calculate. The time is fast. So that was the gap. So it's from second map, not first map. Now what is the property of that? The property is this map. This map you have true density plus noise, like we showed earlier. So they like this. So you put this, you can separate them. But this the from true protein density sum. But this one sum of the noise, constant. So this boundary map is insensitive to noise. Because we need something as a guide to trustworthy at that time. The filter has to be trustworthy. So this is very insensitive noise. So that's good. But it is real by setting the threshold of the density level so that the fractional number of breakpoint filling that density correctly solvent content. Because they have 50% solvent content, that means use a threshold, 50% below that, and 60% with 60%. Just like in the lake, you put the lever up, bottom, and down to define the shoreline. Density field is from this molecular boundary information. So let's see how effective it is. This is a map. There are protein part and solvent part. We couldn't really tell. Perhaps these are, but then you don't really need them. So it turned out that the first filter showed this region the protein region, the right solvent. Of course, it's not quite good. But the second time, getting better. And the third filter, you can see that even the second time is almost converged to filter. So this computer simulation of RG that the 11 residue two sulfurs by sulfur IS method in 1982. Because that solver, this is the method I need something to do, but I really couldn't get any real data. So this is calculated at copper reduction, to calculate unknown scattered data, positive and negative. And before the iteration, it's like this. After one cycle, you can see it's get better. After three filter for three cycle, you can see this and refine the map almost identical. So I know that I sort of know that if it's very weak, as long as we have accurate data, I mentioned accurate enough, that we can solve with the data. Well, I wrote a program called ISI program, but there are several features here I never really publicized. I call it less known, but I thought I should point out now. In the column here, I have a resolution cutoff data. But here, this second column, you can put 1, 2, 3, 4. One is phase filtering for paired SIR or acentric ISA data. Second, phase extension to include incomplete SIR. For some reason, you couldn't get the derivative or native. For centric, we can phase centric. So in the default, I equal to 1. But if you SIR data or if you have a anomalous data, we want the centrics like that. But here, it's a structure factor and phase extension and observed refraction. Now, I did not publicize this because I found it very useful structure factor extension. In other words, we create a structure factor. When then observed, we can do that. In what situation be useful? At the low angle refractions, because of that time, sometimes the bin stop cut off the refractions. But if we improve those refractions, by map inversion for high resolution data, very accurate. You go high is not accurate, but back is very accurate. So sometimes I improve that and it change the map quite a bit. I don't ever mention it because, you create a structure factor. This is something at that time, normally people believe it. You do that when you know what to do. Otherwise, you might misuse it. So I never really published that. But nowadays, you can see that several years ago, we call fragment sensing here. The program, the variable, some other people, you have an old program, you can just put 3, do your free lunch with this free program. So that's the one that I like to mention, that it was PMP because I know that there's potential, but it hasn't built the timing, not quite. Because I want to emphasize this base ambiguity problem. Another is about handedness of anomalous scattering. This is my notebook in 1982. As handedness from the SS data. I said, it's like that. But when the anomalous scattering data change hand, what's going to happen? Phi become pi minus phi. If we reduce this, we have this equation. Now this equation, you know this one here equal to -1, so you have a negative sign in front. Here, not quite easily, but hit conversion. Rho is not a mirror image of that. It is a reverse density of a mirror image. What does that mean, reverse density of mirror image? I won't say the next one. Next slide. This was the talk about the first the discussion in 1989 in the anonymous guesting in Alabama ranch about Steve Ehrlich. And those of us wasn't sure what year. I think it's 89. And also represented here another. You see that this one this is wrong. Equal to what? If the correct one, mirror image minus sign. Listen, what that means is this is the correct one. Mirror image, you put this on the left side. Yes, put the left side. But flip over. The positive density and negative density. So after solving it and cut out, you receive the top. And here is the bottom. So you can see a map still very good connectivity, but it's wrong. So when you run map here, by map inversion like that, you will probably see the statistics. So we'll repeat like that. For example, in this case, many cases, figure mirror and happiness beginning it's an 82 and 80, but beginning. But after this several cycle, this changed to 82. This is increased too, but it's not as high as that one. But R factor is lower. A correlation coefficient 96 and 94. The correct one always bigger, and the R is smaller, right? So this is a small statistic. Is that significant? Yes. The reason is the protein is a protein and solvent. So protein just flipped. So you calculate structure factor, it doesn't change that much. But detail will tell you. So that's what in the program we decide the handiness was such a way to determine it. So that's early work in the 80s. Now I'm going to fast forward to 1997. That's a year that we formed the CIRCAT. And as you know, that CIRCAT right now we have a lot of degree automation and very productive. So I'm going to start from there because also at that time we also get the chance to begin to use the facility in APS. And that was very useful for us solving the first structure in software phase. So in 1999, with 17 years later of the simulation, we solved a new structure by software for the first time. I have to say, before this time, there's also by several structures solved as Sweet Daughter and others. People had done that, but it's all on the known structure. But this is the first time with this song flattening is the for unknown structure. And we had to go to many bin lines, finally get a set of good data. And this is the one, this map is real. You can see the side chain. It's almost like every frame map. So the structure solved. And the wavelength is 1.75, we use that. So now we'll go back a little bit about the structure solved by ACA data. In 1990, we solved a structure using the home source is Arlene. This is a neurophysin. And we solved so the properties of PNS pattern is the structure determined by single wavelength. I don't want to use the popular ion. And then in the A, around that time, with your home source, we solved the human therapeutic. This is about 86 kilodalton. And then we solved the structure here we just mentioned. Now, so based on this result, a request was included in the structural genomics proposal NIH 2000 for the development of direct crystallography. So we think it's the time that we should think about this. So what is direct crystallography? So in the rest one-third of the time, I will talk about this current status and the future perspective of direct crystallography. So how to define direct crystallography? Is the right approach for protein crystallography. Because you unlabel the native crystal and send the wavelength X-ray. Because lots of proteins, about 30% of protein already has matter there. Let's try and use this method already. So this is not just crystallographer, but also biochemist. When it's isolate protein, be sure to include in those, trying not to get rid of a fun way to retain that. And also nearly all atom protein has sulfur. So if sulfur phasing is successful, then virtually any other anomalous scatter become sulfur. So that's that kind of problem. Still have the two questions. Can we use single wavelength X-ray? Can we use sulfur atom routinely? So I'm going to answer this question first. Can we use a routine method? This is much weaker than the selenium. I said not yet. But it is promising because I will show you what it is, why. You can see how small it is at the home source, 1.5, even only 0.5 compared to selenium. Even at the 1.74, 0.9. Well, about the single wavelengths. It was not quite clear at that time to the community, but now definitely is yes. If we look at the number of structures of the MAD phase and SAT phase in the last few years, before year 2000, one was flat, but then the MAD decreased, SAT increased across over here. For our result for the last 7 years, 6 years, we have sort of SAT structure 73, MAD 7. The ratio is 10 to 1 more. And there are 12 by sulfur and the others. So now about the use of number wavelengths. With the increased interest in single wavelengths anomalous scattering data, data collection use of one electron X-ray lineage has become an option instead of a requirement. So we need to optimize our beamlines in all the wavelengths, 1 to 2.5 like that, but not all beamlines we can do that yet. So the home source, we bought a home source, well, not bought, we actually start out with put different parts together, like wavelengths, and in February of 2003, and we use but also use a test bed to circuit soft X-ray development. So pretty quickly we solved a structure home source, and this one here have 150 residue, only 3 sulfur. So that's home source. Then we solve a separate structure on synchrotron. We just show you one of the case, which we think is very interesting. This example is an average quality equation. For people in front, you will see how you don't see too much slide here. But we solved. This morning, my student gave a talk. Now, so this is sample with the 2 data set, but average wisdom. Okay. So we're doing this. I'm very quickly. So what this is a 2 crystal averaged for average equality. So if quality is even worse than average, then maybe use 3 or 4 crystal. So the idea was do a sigma database collection that each one will give a signal, but accumulate. This is the one we want, but we need to monitor that. So 84, we use this number, which the ratio of eccentric. This has been used many people before, like Wang, for example, in the company, he report this kind of thing. But not in any program we can output. So we put inside the program, we're able to output now this. I don't have time to do this. But the bottom is eccentric reflection. We know that is 0. That's when this is perfect. So anything we have, we can know it. Of course, we can get velocimeter related also. I'm just very quick now. But this shows that we require the signal is about 50% of level by this analysis. In other words, we do not really want that much. Generally, the signal ought to be the same as noise. I said, no, we do not need that. That was too good for us. You can provide a signal almost like half of the noise. We can solve the structure. So we are in the borderline, how to reduce the noise level to able to twice as the signal. So this is from here, this equation here. Anyway, so we are developing a program here that with robotic. And then every time we check the signal, if it's good, go away, and finish. If not, cycle back. And the last time I want to mention that community has a lot of interest in non-wavelengths. Last year that we have this one here. And somehow the picture taken here, all the synchrotron people on one side, the home source on the other side. But anyway, it's good. We talk, and yet it's needed. No matter how good is the equipment or program, we need the people interested. We need to talk to everyone. We learn from each other. I think that will achieve the routine software phasing in the very near future. Now I'd like to thank the people that in UJ, John Rose, and it was many years and a lot of good work, and thank John, thank you for, and James, now is in the Institute of Biophysics in China, and Nero now that Ronnie is in Taiwan, and Jeff in ALS, and then Lee Rong, and then and the other people, Gary is here, and she was here too in this meeting. And I would like to thank the Bell Arthur Robin, because he provided us big time crime data on income, the structure of solving income. Turned out that's the best place we got the best monocycle. Okay. And these people were strange. I was quite wonder why, but later on we understand. I don't want to mention some more. That means optimization. If you optimize in one reference too good, it may not be too good in another place. So it's better with something not optimized, then you get a bad data. So the concept, I think, need to be modified. Circuit, John Price, and Rosenberg, and Albert, or Proban, Jim Fay, John Min, and Andy Hopper, and Cassie. One particular thank Cassie because he really is the few with the organization, the circuit, how to run. But she's the one get moving. And Bi-Cheng is in all the Yale, and Edward, and Minro, the structure. And then Chen San-Chen, he's the person, I don't know where he's at now, lost the one. He's the one that helped me to search the habitat table about a year and a half to look at it. So that was the, and also the Bill Furry was the PDP-10 at that time, and we are very helpful, and Martin Sachs, a very wonderful general person, and Chung Su-Yu would all together. Some of you that know that the Pittsburgh Diffraction Conference of Chung Su-Yu Award, he was killed in the Korean airline 007. And then Rikaku, and then they loaned us the first set of mirror. And we got a chromium target from Taiwan because I wanted to try in Taiwan. It was in 1990, but not successful because no mirror. It's just so dirty. So I borrowed that. And I'd like special thanks to Wally Porras, Richard Mark, and my wife, Jana Central. She really supported, and also the funding agencies and the VA, and that's where a lot of work started in there. Thank you.